Hello everyone. Welcome to the talk. I will be presenting this talk on expressive virtual avatars on behalf of the authors who unfortunately could not attend due to a variety of reasons. So virtual humans are becoming essential in many fields. We see them in telepresence and remote work, in entertainment like gaming and virtual events, in education as well as virtual teachers, and even in healthcare as virtual therapists. While the applications for virtual humans are vast, creating them presents significant challenges that have hindered their widespread adoption. First, as we see on the left, there's the uncanny valley challenge, where even small imperfections in an avatar's appearance can make it look fake and break the immersion experience. Second, the process requires immense manual effort, as you can see on the right. This makes creating high-quality avatars slow, expensive, and difficult to scale. Recent works like ASH have pushed the photorealism using 3D Gaussians. However, these methods often struggle to fully disentangle the body motion from facial expressions, which limits true expressive control. While other approaches lack the ability to model dynamic loose clothing and offer inflexible control mechanisms that require images to drive the facial expressions rather than controllable facial expression parameters. To this end, we introduce EVA, a new method that achieves real-time, high-fidelity rendering of expressive virtual avatars with fully disentangled control over the body motion and facial expressions. Our goal with EVA is to create an avatar that is fully controllable, deformable, photorealistic, and runs in real time. In short, we want to be able to drive it using separate inputs for virtual viewpoint, skeletal motion, and facial expressions. Here's a simplified view of that pipeline. We take the control parameters like camera viewpoint, skeletal motions, and expressions, and use them to drive our expressive template, and then use the geometry to generate a disentangled 3D Gaussian appearance model for the final rendering. To train our model, we use data from a multi-view calibrated studio with about 100 cameras. This dense capture allows us to learn a highly accurate actor-specific model for both geometry and appearance. And at inference time, our system is driven simply by the skeletal motion and expression parameters, allowing for real-time animation from any source that can provide this data, like motion capture files or even audio-to-gesture systems. This diagram shows our full method, where the inputs are the camera viewpoint, the skeletal motions, and the facial expressions. And these drive our two main modules, the expressive deformable template, which handles the geometry, and the disentangled 3D Gaussian appearance module that handles the photorealistic rendering. Let's look at the geometry layer first. The skeletal motion drives a deformable body model to handle the clothing dynamics, while the facial expression parameters control a personalized head avatar. These two parts are then combined into a single expressive template mesh. Conceptually, our expressive template mesh is a function of skeletal motion and facial expressions. It's formed by combining a deformable body model with a personalized head model using a specialized stitching operator. First, I will briefly talk about the deformable body model, which is sort of powered by several neural networks that learn to predict deformations based on the driving motion, and it results in realistic geometry and texture that capture the dynamic wrinkles of the subject. Now let's focus on the head. Our key contribution here is a personalized head model that is controlled by facial expression parameters. We build upon the flame parametric model for face. It uses parameters for shape, pose, and expressions to create a detailed 3D head mesh. And to create a subject-specific avatar, we extend the standard flame model by adding learnable per vertex displacements. Which allow us to capture the fine person-specific details like hair and unique facial features that the base model cannot represent. First, we align and optimize the global position of the head. And then we use a freeze and refine strategy wherein we freeze the global transformation parameters and refine for the shape parameters of the parametric face model. We use mask losses to fit the shape parameters, which helps with a good fitting. Finally, we optimize the vertex displacements to capture the high-frequency details. And for this step, we use weighted fitting to protect the sensitive areas like the eyes and the mouth. And this results in a highly accurate geometric representation of the actor's head. Here we see results of our head modeling pipeline, which creates a model that is both accurate and expressive. So on the left, the heat map shows the geometric error, and as you can see that adding our per vertex displacements improves the accuracy of the fit to the actor's scan. And on the right, we demonstrate that our model is also expressive, and it's capable of generating a wide range of facial expressions. Once we have the deformable body and the personalized head, we use an automated stitching operator to seamlessly combine them into a single watertight mesh. And this gives us one unified template that is fully expressive. Now for the appearance model, the expressive mesh we just created serves as the geometric foundation. And we render this 3D mesh into the 2D UV space to create the motion-aware textures specifically for each pose. And these are position and normal maps that encode the character's exact geometry for a particular pose. And these maps are then fed into two separate units, which is our key step for disentanglement between the body and the face. So one network predicts 3D Gaussian parameters for the body based on the body motion, while the other independently handles the face based on the expression parameters. Finally, these predicted Gaussians are transformed from the template's UV space into the final pose space using a skinning operator and rendered in real time via 3D Gaussian splatting to create the final photorealistic image. The critical step here is the disentanglement, where we use two separate units, one to predict the body's appearance based only on the skeletal motion, and the other predicts the head appearance based on the facial expression parameters. And this explicit separation is what prevents artifacts and allows for independent control. Now let's look at the results. So here is a result showing novel view, novel pose, and novel expression synthesis of separate actors. And our model handles complex interactions of motion and expressions, generating photorealistic results from arbitrary new control inputs in real time. When we compare EVA to the prior state-of-the-art methods like DDC and ASH, the difference is clear. While they produce good results for the body, they fail to capture the detailed face expressions because they lack our explicit disentangled face model. EVA produces much higher fidelity results, especially on the face. The ability to disentangle can be seen in this result. Here, what we do is we take a single body motion and apply different facial expressions. Our model also allows for easy retargeting, where we can take the performance of a driving actor and reenact it on two different avatars, each preserving their unique appearance while faithfully following the motion and expression commands. Our approach does come with its limitations, such as handling topological changes. For example, in this slide, the subject is changing the state of their clothing, and our current pipeline does not account for such changes. Second, our model is a personalized model and requires per subject training data captured in a dense multi-view capture studio. And future works could look into generating high-fidelity full-body avatars from just a single camera. To conclude, we introduce EVA, a new framework for high-fidelity, real-time digital humans. And our system gives you full independent control over the avatar's bodies, hands, and face. And our contribution is a two-layer model where we start with an expressive deformation template for accurate geometry, which then guides a disentangled Gaussian appearance model. And this separation ensures clean, independent control over the body and the face. And to make this possible, we also created a new data set with 4 actors, which we will also release. Thanks for your attention, and please scan our QR for more details.
Thank you, Karthik. So that concludes the presentations for this session. So let's thank all the authors and the presenters once again for the wonderful work and the presentations. I also want to thank the tech admins who ensured that everything went smoothly and there were no technical glitches with the presentations. I invite all of you to engage with the authors outside in the interactive poster session. So as you exit, it's on the right side. Thank you, everyone, for attending.